The fact that dense soils under low confinement tend to dilate has some important implications. Originally, this was studied because grains were being sold by volume, and a volume that would be shipped of grains after some vibration, it could eventually occupy less volume. However, the mass was preserved, but if you sell by volume, then the issue of whether you have delivered what you have promised is problematic. The problem that granular matter may densify under vibration, it can go also the other way. For example, you may have a granular base that is very well densified. However, you come in with a vibratory system that may actually loosen it. And even though we have recognized this extensively in the material science, you still go, for example, to cooking recipes, and the quantity of flour or sugar, etc., may be specified not by weight, but by volume, like a cup, and that creates some uncertainty at the time of cooking. So really what we need to do is specify things by mass. But there are other implications of contractive and dilative tendency. Let's consider the following case. Imagine that we have several masses that we're going to tow, and they are connected with springs. And at the base of each of these masses interacting with the surface, we mobilize a resistance that looks like this, with a post-peak strain softening. So now we could think of two cases, one in which the springs are perfectly rigid. So as soon as I begin pulling here, and I'm going to plot the force T with respect to the displacement, as soon as I begin pulling, every single one feels the action of the pull, and every single one begins to move along this line. So if this is the deformation at peak, and this is the deformation at residual condition, then I'm going to generate exactly that response, but 4 times higher, because they are all adding up. And once again, this is going to happen at delta peak and at delta residual. And the only difference is that T will be equal to all the values in T at any deformation delta will be equal to n values of the individual elements, T individual at deformation delta. This is if it is perfectly rigid springs. Now, what happens if the springs are very soft? Well, I'm going to pull the first one, but the spring will begin stretching, but I'm not going to mobilize any strength in the second one, or in the third, or in the fourth. Eventually, when I begin pulling, eventually I overcome the peak, and the element will move fast towards me, stick-slip type of motion, and then it will transfer some of the action to the next one. And so what I'm going to see is that the displacement is going to go softly to T peak, and then it's going to drop, and then it's going to pick up the other one, and then it's going to drop and pick up the other one. And in the end, the value that I measure here is indeed T residual is going to be n times the individual T residuals. But the peak never reached the peak of all of them working together. This is a form of progressive failure. And in progressive failure, I can count on the residual strength of all the components involved, but I cannot really count on the peak strength. So now I'm beginning to have a problem, which is my ability to predict what is the true strength that will be relevant for a large engineering application when I start from a small laboratory specimen. And it may turn out that my measurement, the peak strength, becomes specimen size dependent. Materials with post-peak strain softening could lead to other potential implications. Imagine that I have a specimen that I'm loading under isotropic confinement, and then I apply the deviatoric loading, but any other type of loading will also apply, not only axial compression. And for some spatial variability in the system, then this point reaches peak conditions. And therefore, this point is ready to go over the hump, but if it's going to go over the hump, these are local stresses and strains, is going to transfer the load that is carrying to the neighbors by compatibility of deformations. So now the neighbor gets loaded, and the neighbor goes through a similar sequence of events, and then what this will lead by this positive feedback mechanism that there is a shear band of failure. And so positive feedback leads to strain localization. And the consequence of that is that the volume change is going to happen only along this band, because once strain localization happens, the upper block and the lower block will work pretty much as rigid blocks. Could be a piece of rock, and it's just going to displace along the shear band. And therefore, when this happens, you may not be able to measure, or you will not measure properly, the changes in volumetric strain. What you measure on the outside is not reflective of volume average processes, and furthermore, it will be a diminished quantity because those changes are particularly occurring along a band. Summary: whenever we see materials with post-peak strain softening, whether in drain or undrained behavior, with cementation, without cementation, or unsaturated behavior, under many conditions we may see this type of behavior, we have to be very careful with localization and the implications of localization. Localizations are ubiquitous in soils. We have to be very careful how to analyze them, and there have been beautiful mechanical developments. For example, the classical work by Rudnicki and Rice, and many experimental studies that have followed. There are other implications of dilation. So let's explore the following one. We go back to the QP tau sigma space, and this is void ratio. So this is the projection of the ultimate failure line in tau sigma QP and in E sigma or EP. And let's assume that we have specimens, several tests, and we're going to run 10 different triaxial tests at the same void ratio, but at different confinement. In other words, these specimens to the left of the failure line, of the critical state line, specimens are in the dilative regime, while here they are in the contractive regime. So in the contractive regime, all the specimens to the left will go to the failure line with constant volume shear, but these specimens will experience dilation. And the angle of dilation will add to the constant volume friction angle by 3/4 or a certain fraction of the angle of dilation. And the angle of dilation in a very densely packed, under low confinement conditions, could exceed 30 degrees. It has been measured. And it can be predicted if you do the analysis for a cubic tetrahedral packing trying to come out of that packing. And so at the origin, we're going to add up the dilation with the constant volume friction angle, and we're going to have a peak friction angle, peak strength line somewhere there. And then as for a material at higher confinement, the dilation will be lower, so the peak will be along this line, will be lower. And so if I draw the envelopes where the points are failing, I may get something that looks like this, where this line at the origin is very steep. Could be 60 degrees or more. And so one consequence of this is that the envelope, the failure envelope, is not necessarily a straight line if you are looking at the peaks. If you are looking at constant volume shear, it's pretty close to a straight line, but it may actually be a curved failure line or failure envelope. The other consequence of that is that if you just look at the narrow region of the material response, you may be tempted to use a straight line to capture the strength. And that straight line will look like an intercept y equals a plus bx. In other words, that will give you a tau ultimate equal to an intercept plus sigma effective tangent phi. And that is very tricky because really we were testing a sand. You can pick up every grain from each other. There is absolutely no cohesion. This was just a consequence of the curvature of the failure line because of adding the angle of dilation. And so the consequence is that sometimes we refer to soils as cohesive and cohesionless. Both are terrible words to use because they put the wrong state of mind in how we understand soils. We have to start from a basics that under most conditions, soils are granular materials and their strength is purely frictional. Now, there may be other effects. There may be electrical forces. There may be early diagenesis. There may be capillary effects. There may be the curvature of the failure envelope. But if we assume that there is cohesion, and we put that cohesion in the bearing capacity equation with the three terms, with a cohesion and a friction component, we are going to be looking for trouble. We are going to be in a very dangerous territory. In fact, there have been studies that most of the failures, for example, of retaining walls, is when either the backfill or the foundation were assumed cohesive sediments. Please let me insist. The word cohesion should not be used in the study of soils. And we should be referring to fine-grained soils or coarse-grained soils. And we should totally avoid the terms cohesion or cohesive and cohesionless. This is very misleading and incorrect. The next observation I would like to make is that at low confinement, given the same void ratio, at low confinement the soils will tend to be dilated, yet contractive at large confinement. So let's take this graph and rotate it 90 degrees to analyze the following condition. Imagine that we have the subsurface and the water table is here. This analysis would tell me that the void ratio versus sigma z plus 1 times k naught, that one will give me the mean stress, but divided by 2. So I could draw this line in this space to look like this. Now, if the soils are all at the same void ratio, then I could anticipate that the upper part of the sediments are going to be dilative, while the lower parts are contractive. That means liquefaction does not happen in the shallow layers. It happens 7 meters, 10 meters, 15 meters down, where there is enough confinement for the materials to become contractive. Now, there may be manifestations of liquefaction at the surface because of sand volcanoes that form and break through this slab that is going to be floating on top of liquefied material, sometimes for hours, until all the excess pore pressure dissipates. So the depth of liquefaction is below some critical depth. Now, at the same time, I'm going to refresh another concept, which is the idea of threshold shear strain. If I plot during an earthquake the shear strain goes something like that because there is a whip effect because of site amplification. So this is the shear strain. So there is a minimum shear strain that is required for volume change. you may go back to earlier presentations where we were talking about these threshold strains. And if I plot that threshold strain, this is gamma threshold. This is not unit weight, please. This is shear strain. So below this level, there can be no liquefaction because there is no enough strain to cause volume contraction. Summary. There is a depth for liquefaction to take place, which is below the region where the sediment is dilated and above the depth where there is enough threshold strain to cause volumetric changes. So combining simple concepts that we have already discussed, it brings huge understanding into many different aspects of soil behavior.